Let us consider an economic interpretation of the constraint minimization problem. So let the decision variable x be the volume of some product produced by a factory. So if we look at the minimization problem, minimizing f of x, so the objective function is maybe the cost of operation to produce x units of this product. So we're trying to minimize the cost of operation. Subject to the constraint g of x is equal to 0 is maybe some target output that has to be met. And then h of x less than or equal to 0 maybe represents some constraint on resources. Now, instead of thinking about it in this constraint optimization form, let's consider a different scenario. So instead of trying to meet an output target exactly, what we do is that there is a cost associated with not meeting the target, and that cost is mu times g of x. So if mu is greater than 0, that means exceeding the target results in added cost. So maybe if we produce more than is necessary, then we have to pay some inventory costs. And falling short of the target reduces the cost. So for example, maybe if we produce less than what's necessary, we have some extra storage left, inventory storage that can be rented out for some price. So and then mu less than or equal to 0 can also be attributed a similar kind of interpretation. So we're not trying to satisfy a constraint, but we associate a cost with not satisfying the constraint. Similarly, for the resource constraint, we don't have to satisfy the constraint exactly, but there is a cost associated with exceeding resource limits, which is lambda times h of x. In this case, of course, lambda has to be greater than or equal to 0. And if resources are not consumed, we assume that they can be sold for the same price, lambda times h of x. Now, there is a supplier who sets the prices mu and lambda for these resources, because the associated with the target constraint, we can also think of it as a resource. For example, the storage space can be thought of as a resource. So there's a supplier who sets these prices. So from the factory's perspective, the total cost is now f of x, which is the operation cost, plus mu times g of x, which is the cost of not meeting target exactly, and then lambda times h of x, which is the cost of violating the constraint on resources. And this cost is nothing but the Lagrangian, we see. So for a given mu lambda set by the supplier, the factory tries to minimize the total cost. So we can write this as minimize over x, the function L of x mu lambda, where mu and lambda are given for this minimization. And this is an unconstrained minimization, because mu and lambda are given, we're just minimizing over x. Now define this new function k of mu lambda equals the minimum over x of L of x mu lambda. So given a mu lambda from the supplier, the factory minimizes over x, and that minimum cost is k of mu lambda. So from the perspective of the supplier, what should the supplier do to maximize his profits? He should set the prices mu and lambda so as to maximize k of mu lambda, subject to lambda equals 0. So we see that associated with our original optimization problem, we have kind of an associated optimization problem, which we call the dual. And we see that this is kind of a min-max game between the factory and the supplier that eventually sets the prices. So this dual optimization problem occurs in many situations and has many useful interpretations. And the dual actually is very valuable because it adds insight and understanding into the optimization, as well as provides strategies for doing computations. So we'll encounter two examples of dual problems, one in connection with energy theorems and another in connection with limit analysis. And our discussion of dual problems will be limited simply to these two examples, although duals are a very powerful idea.